Welcome to the deep dive.
hmm
Have you ever been hiking up a mountain and wondered why, even though you know warm air rises, it just gets colder and colder the higher you climb?
Yeah, it definitely feels a bit backwards, doesn't it?
Or maybe on a plane, you know?
Yeah,
You take off from somewhere warm and up at cruising altitude, brr, it's chilly.
exactly.
Well, that seeming contradiction is exactly what we're going to unpack today.
And it all started with a fantastic question.
Yeah, from Ollie in Christchurch, New Zealand, he asked, if heat rises, why does it get colder as you climb up mountains?
It's a brilliant question, Ollie, and actually a perfect way for us to get into some really fundamental stuff about our atmosphere.
Mhm.
We've got some really insightful material here, particularly an article called The Science Behind Thermals, How Warm Air Rises and Creates Buoyancy.
Okay.
And what's fascinating, really, is how this, well, seemingly simple idea, warm air going up,
Mhm.
is actually the engine behind so many weather things.
Like what kind of things?
Well, from, the gentle way clouds form all the way to the power of rain and even lightning. It all stems from this.
Wow. Okay. So that's our mission then, to connect those dots.
Exactly. We want to help you clearly understand this interplay, why warm air rises, why it cools down higher up, and how all that creates the weather we see. Get those aha moments going.
Okay, great. So let's tackle Ollie's question head on first. Warm air does rise. That part's true, right? People talk about thermals.
Absolutely, yes. That
Yes.
part is definitely true. Think about glider pilots.
Right. They use them to stay up.
Yeah, skillfully using these like invisible elevators of warm air to stay airborne for ages without an engine. It's pretty amazing.
Okay.
Or, those huge birds like South American condors, they soar for miles, barely flapping.
Riding the thermals.
Exactly.
Yeah.
They're using that rising warm air to conserve energy. So, yeah, that upward movement of warmer air, it's a very real thing happening all around us.
Okay, so if the warm air is definitely heading upwards, why the chill? Why does it get colder as we go higher? That's the real puzzle Ollie's getting at.
Right, here's where it gets really interesting. So, when that pocket of warm air rises, it finds itself in, well, a different environment. The air pressure is lower up there, significantly lower.
Less air pressing down from above?
Exactly.
Hmm.
Now, picture that bubble of rising air. As the pressure around it drops, the bubble, it expands.
Oh, like a balloon. If you let it go and it floats really high up, it gets bigger.
Precisely. That's a perfect analogy. And as this air expands, the heat energy it contains gets spread out over a much larger volume.
Okay.
Think of it like taking the same amount of butter and spreading it over a bigger piece of toast. It's thinner everywhere, right?
Right, less concentrated.
Exactly. So with the air, the molecules spread out, they have fewer collisions, and the overall temperature drops. And this cooling effect, just from expanding into lower pressure, is usually way more significant than the initial bit of warmth that made it rise in the first place.
Ah, okay. So the very act of rising and expanding makes it cool down. That's key.
That's absolutely key.
But wait, where does that initial warmth come from then? What kicks off the whole rising process?
Good question. That takes us back down to the ground. The article points out something important. The sun doesn't really heat the air directly very well, at least not in the lowest part of the atmosphere, the troposphere where we live.
Really? I always thought the sun heated the air.
Well, it heats the surface. The land, the oceans, the roads, buildings.
Mm-hmm.
The ground gets warmed by the sun's radiation.
Okay, so the ground absorbs the heat first.
Yes. And then the ground heats the layer of air directly touching it.
Ah, like a frying pan heating the food that's sitting on it.
Exactly. Or like a pot of water on a stove. The burner heats the bottom of the pot, right?
Mm-hmm.
And then the water touching the bottom gets hot and starts to rise. It's the same idea with the air. The warm ground heats the air right above it. That air gets less dense than the cooler air higher up.
And so it floats upwards. It's buoyant.
Precisely. Like those bubbles rising in the pot of water. That's how the whole thermal process gets started, heating from below.
Okay, ground heats the air rises, expands, cools. Got it. But doesn't the Earth also, like, radiate heat back out? How does that play into it?
Yes, absolutely. The Earth absorbs the sun's energy, warms up, and then sends some energy back towards space, mostly as infrared radiation. You can think of it as heat.
Okay.
Now, this is where greenhouse gases come in. Certain gases in our atmosphere, water vapor is a big one, carbon dioxide, methane,
Hmm.
they're really good at absorbing that outgoing infrared heat radiation from the Earth.
Ah, so they trap some of the heat that's trying to escape, like a blanket, kind of?
Exactly like a blanket. That's a good way to put it.
Weird.
And this absorption of infrared is another way the air itself gets warmed up. But here's the thing.
Hmm.
The concentration of these greenhouse gases is highest near the ground.
Oh, right.
So again, most of that infrared absorption and warming happens closer to the surface. It just reinforces that idea of the atmosphere being heated primarily from the bottom up.
Which leads back to that warm, buoyant air near the ground that wants to
You
rise.
got it. It all fits together.
Okay, so we have this established pattern.
Mm.
Warm air rises, expands, and cools. Is there like a standard rate for this cooling? I think the article mentioned a specific term, lapse rate.
Yes, exactly. Lapse rate. That's the meteorologist's term for how quickly the temperature drops as you go up in altitude.
And is it always the same?
Well, it varies a bit, but for dry air without much moisture, it's pretty consistent. It drops by just under 10 degrees Celsius for every kilometer you go up.
10 degrees Celsius per kilometer. Wow, that's quite a drop.
It is. Or you can think of it as roughly 1 degree Celsius cooler for every 100 meters you climb. You definitely feel that on a tall mountain.
No kidding. Okay, but you said dry air. The article mentioned water vapor changes things. How does moisture affect this lapse rate?
Ah, yes, water vapor. This is where clouds come into the picture, and it's really quite fascinating. So you have your warm, moist air rising and cooling. As it cools, its ability to hold water vapor decreases. Eventually, it gets cool enough that it just can't hold all that moisture anymore. So the excess water vapor has to turn back into liquid water.
Condensation, like water forming on a cold glass.
Exactly like that. And those tiny liquid water droplets are what we see as clouds.
Okay, but does that condensation do anything to the temperature?
It does. This is the clever part. When water vapor turns back into liquid water, it releases heat. Remember how it takes energy to evaporate water?
Yeah, like boiling a kettle.
Right. Well, condensation is the opposite process, so it releases that stored energy back into the surrounding air. It's called latent heat.
Latent heat. Okay, so condensation actually warms the air up a bit?
Just a little bit, yes.
Yeah.
But enough to counteract some of the cooling from expansion. So when condensation is happening, when clouds are forming, the rate at which the air cools with height slows down. The lapse rate becomes less steep.
So what does it become then on average?
On average, in moist, cloudy air, the lapse rate is closer to maybe 6.5 degrees Celsius per kilometer. Still cooling, but not as fast as dry air.
Interesting. So the very act of forming a cloud changes the temperature profile.
It absolutely does. Clouds aren't just passive things floating up there. They're actively involved in the energy balance of that rising air.
And these clouds formed by rising thermals, they're often those puffy cumulus clouds we see, right?
That's exactly right. Cumulus clouds are basically visible thermals. You can see the rising columns of air marked out by the cloud.
Why do they have those lumpy cauliflower-like tops sometimes?
That's because the rising air isn't perfectly uniform. Some bits might have slightly more moisture or be slightly more buoyant, so they condense earlier or rise a little higher, creating those characteristic bumps and textures. It's showing you the dynamic, turbulent nature of the rising air.
Cool. And I guess if there's a lot of moisture and the air is really unstable, these can grow much bigger into storm clouds.
Absolutely.
Yeah.
If you've got plenty of moisture down low, and the conditions are right for that air to just keep rising rapidly because it stays warmer than its surroundings for a long way up, then those cumulus clouds can grow vertically into enormous cumulonimbus clouds, thunderstorm clouds.
Yeah. The anvil.
Exactly. The tops of these can reach way up where it's well below freezing. So you get ice crystals forming up there alongside supercooled water droplets.
And that leads to?
Well, collisions between these ice particles and water droplets start separating electrical charge within the cloud.
Yeah.
Positive charge tends to gather higher up, negative charge lower down.
Yeah, creating a giant battery.
Essentially, yes. And eventually, the difference in charge becomes so great that you get a massive electrical discharge to equalize it. That's lightning.
Wow.
And of course, these big clouds are where you get heavy rain and sometimes hail, which forms when raindrops get carried up into the freezing parts of the cloud repeatedly, adding layers of ice.
It's really incredible how it all links back: warm air rising, cooling, condensing, leads all the way to lightning and hail.
It really is interconnected. That fundamental process drives so much complex weather.
Okay, so let's loop all the way back to Ollie in the mountains. How does all this explain why it's cold up there?
Well, connecting it all back, the simplest answer for Ollie is this. When you climb a mountain, you are literally moving up into layers of the atmosphere that are naturally colder because the air pressure is lower there.
So it's not just that the rising air becomes cold, it's that you're entering a region that's already colder.
Exactly. Remember that lapse rate.
Yeah.
Temperature decreases with height. You're just ascending through that gradient.
Okay. And even if warm air does rise off the mountaintop itself.
Right. Even air starting its journey from a high elevation is beginning in a lower pressure environment. So it's already cooler than air at sea level to begin with, and it will cool further as it rises from that point.
Makes sense. And that extreme altitude effect, like on Mount Everest, the thin air people talk about.
That's directly related, yeah. The air is thin because the pressure is so low. There are just fewer air molecules, including oxygen molecules, in each breath you take. That's why climbers need supplemental oxygen up there. The low pressure dictates both the low temperature and the low oxygen availability.
And that cold is why snow and ice can stay on mountain peaks all year round, even in summer sometime.
Precisely. The altitude keeps the average temperature below freezing for much, if not all, of the year, preventing significant melting.
Mhm.
It's a direct consequence of being higher up in that cooler part of the atmosphere.
So to sum it all up for Ollie and everyone listening, warm air does rise because heating from the ground makes it less dense. Check.
Check.
But as it rises, it moves into lower pressure, expands, and this expansion makes it cool down significantly.
Yeah, the expansion cooling effect is crucial.
The atmosphere is mainly heated from the ground up, reinforcing this whole process. And this natural decrease in temperature with height, the lapse rate, explains why mountains are cold. You're simply climbing into colder air layers. Plus, this whole rising, cooling, condensing process drives cloud formation, rain, and even thunderstorms.
That's an excellent summary. It really covers all the key pieces.
Right.
Ollie asked a deceptively simple question that gets right to the heart of how our atmosphere works.
It really did. A fantastic question that led us down a fascinating path. And it makes you think, doesn't it? About how these fundamental principles of air temperature, pressure, and movement scale up to influence, well, everything. Huge weather systems, global climate patterns, they all rely on these basic physics.
Absolutely.
What other seemingly simple questions about the world around us, might have these really deep, complex, and fascinating explanations just waiting for us? Something
Yeah.
to ponder. Thanks for taking this deep dive with us.